Yes, so our next speaker is Gabriel Dizon from Philippines, and he is going to talk about primordial black hole abundance constraints, mainly projections for binary mergers with unequal mass ratio.
Okay, thank you, Anish. Thank you as well for the invitation to this talk. So I'll be talking about something fairly niche, which is primordial black hole abundance constraint projections specifically for binary mergers with unequal mass ratios. This is based off my PhD dissertation, and I am formerly from the National Institute of Physics of the University of the Philippines. Currently, I'm looking for a postdoc. So with that out of the way, here's the outline of my talk. I will first introduce what is the pretty much main motivation for this sort of study. Then I will outline as well the model for PBH binary formation. I will skip the entire formation process and go straight into how PBHs actually form binaries, and then how or when do they merge, as well as was the distribution of their mergers. Then I will discuss the constraints that you can get from gravitational wave observations from PBH on PBHs if we assume a extended mass distribution for them. And then after that, I will also discuss the constraints that you could generate, or rather that you can project, if you assume that they have some sort of a mass ratio dependent clustering. So let's start with the introduction. So the overall motivation of this study is that, okay, we have gravitational waves, we have actually started observing them. And because of that, there has been a renewed interest in primordial black holes in particular, because they could form a portion of whatever gravitational wave signals we managed to observe. So here we have an image of the LIGO-Livingston detector, and then hopefully in the future, we'll also be able to get data from the future Einstein telescope. Now, because of gravitational wave astronomy, we have several avenues of exploration that we could test. So we could perform tests of gravity at the weak and strong field regimes. We could also use it to probe the neutron star equation state. And for the purposes of this talk, we'll be using it to probe dark matter candidates, in our case, primordial black holes. Now, in this talk specifically, we're going to explore the impact of considering basically a wide range of unequal binary mass ratios. The reason why we are considering this range, 1 to 1,000, is because most previous studies, at least to my knowledge so far, is that usually they only explore up to the mass ratios of Q equals 10, Q equals 18. And that's basically because of the limitations of how we model our detectors. Some are detectors usually, or rather waveform templates, usually only go up until to like Q equals 18. Much recently, however, we managed to go up to Q equals 1,000, and so why not? Why don't we just take the entire range that we have available? And then we take that range and apply it to primordial black hole abundance constraint projections. Specifically, we're considering projections for LISA and the Einstein telescope specifically, because these possibly are projected to have some of the widest observation windows, at least when it comes to mass. Now, what we've noted with our studies, two papers in particular, is that for the first one, the constraints are relatively robust if we only change the distributions that we consider for our merger rates. So for both LISA and Einstein telescope, we don't really observe much of a change with how the constraints behave. If we do incorporate a clustering, however, then we find that we do have a slight enhancement of the two-body merge rate, at least for lighter binaries, which also reflects in the projected constraints. And then I will also touch upon the difficulties in general of modeling the merger rates for unequal mass ratio binaries, and then some possible approaches that we could take in order to deal with them. So let's go straight into how the primordial black holes form binaries, and then how do we also calculate for the merger rate. So the historical background in general is just that they were first hypothesized by Zeldovich and Novikov back in the 1960s. They form from curvature fluctuations, which have been discussed in the previous talks. And then Hawking posits that, okay, there should be signatures left of a black hole evaporation as well if you have primordial black holes existing with masses lighter than 10 to the 15 grams. And then later on, so a lot of surveys on microlensing have been conducted, and not just microlensing, actually. We also have surveys on CMP, surveys on white dwarfs, etc., that set fairly robust constraints on primordial black hole abundance. Now, skipping the details of primordial black hole formation, let's assume that they have formed, and let's assume that we have two primordial black holes in fairly close proximity to each other, forming relatively early on in the universe, let's say at radiation-dominated era. And let's assume that they are gravitationally bound. So from there, we can define that the initial co-moving PBH binary separation, X naught, is given by this volume over here. So it's primarily dependent on the total mass and the energy density, as well as the average over density of the binary pair. If we assume a isotropic matter distribution of the binary, about the binary, then the tidal forces, at least the radial tidal forces on that binary, are negligible. So the radial evolution is simply dictated by both Hubble flow and the self-gravity of the binary itself. The angular momentum then is obtained through the angular component of the tidal forces on the binary, which are not negligible. And it's given by equation 3. And then you have the dimensionless, you could recast it as a dimensionless angular momentum given by equation 4. So we have a formula for the semi-major axis. We also have a formula for the angular momentum. From there, if we select for binaries that merge within the time of the universe, or at least up to the time of the universe, current age of the universe, we can set constraints on what our X naught and our J should be, and we'll be able to compute for the merger time for at least specifically a highly eccentric orbit, since we expect those to merge the quickest, given by equation 5. Now, given that we have a set of parameters, we now want to know the distribution of those parameters in order to determine a population of primordial black holes that would merge. So let's say you have a configuration given by this diagram over here. X naught represents the distance between the binaries themselves, and Y here determines the distance to the next nearest neighbor of your binary. So you could define a differential binary number density given by equation 6, which is where you have n, the n of m here is your differential co-moving PBH number density. Basically, just tells you how many PBHs there are of a particular volume of a particular mass. N bar here of Y is the expected number of primordial black holes within radius Y, and N is the average number density across, like, we treat it as a global quantity. So then this entire component here is the differential probability that you will find a binary with mass M1, mass M2, separated by a distance X naught. And then here, e to the negative n bar y assumes that your primordial black holes are spatially distributed in a Poisson-like manner. So you have a Poisson count given by this factor over here. From here, we then now can compute for the differential merger rate of your primordial black holes, which is given by first the spatial distribution of your primordial black holes given by the above, equation 6. The distribution of the angular momenta given by dj dp over dj, and then you have a term here, a Dirac delta, which just selects for binaries that are going to merge within the specified time t merge, which is usually set to the age of the universe, although sometimes, or in our case, we might actually set it much earlier, depending on our needs. So if we plug in equations 5 and 6, and from some algebra, And calculus, we get equation 8, where we have simply teased out all of the v of x naught terms when we group them into a singular integral. And then if we try and solve for j, the distribution of the angular momenta following Rydal, we get this expression over here. Now, we don't use this full expression specifically. Instead, we utilize an approximation given by Hutzi. Although, all in all, this is the differential merger rate that we will be working with. The key quantities here are that we have F PBH, which is the abundance of primordial black holes relative to all of dark matter, as well as phi, which is the PBH mass distribution, which we define as this quantity. Of course, the other terms like suppression factor also matter. In fact, they will matter later on once we start accounting for clustering. And these are usually dependent on both on n bar, the abundance, as well as the moments of your mass distribution. So before we move on, are there any questions relating to the derivation of the merger rate? None? Okay. So we can now move on to specifically applying this merger rate over here to constraining the PBH abundance based off gravitational wave merger observations. So, as I mentioned, the key components that we'll be considering here are phi and FPBH, at least for this next section. So, the calculation of phi, or rather, the mass distribution itself, in general, it's given by this quantity, and we formulate it such that we normalize it to unity, enforcing that, okay, we have this form. Sometimes you could normalize it instead to FPBH, but for clarity, we normalize it to 1. And then we can define mass average quantities in this manner, which shouldn't differ as much from the definition over here for the mass moments of our distribution. Now, commonly in literature and in general, people formulate, or rather calculate the merger rate utilizing a monochromatic mass distribution, which just is simply a Dirac delta centered at some reference mass m sub c. So it is the simplest of the mass distributions. It allows you to narrow down and simplify the merger rate significantly. And surprisingly enough, it's also an acceptable approximation for narrow mass distributions for primordial black holes. In fact, up to a certain extent, usually for log normal, it's acceptable up to like sigma equals 2. And for power law, I don't really remember, but around that range as well if you try and perform a conversion. And as expected, the moments of the distribution, the mean is just m sub c, centered at m sub c, and the m squared is just m sub c squared. Now, another distribution that's not as commonly considered, but still considered for mostly non-GW constraints, is the power law mass distribution. So you have this definition for the power law distribution, where NPL here is the normalization, and the exponent gamma relates to the cosmological equation of state at that particular epoch where formation takes place. So it's given by equation number 16. Now, Carr, in their work where they extend the monochromatic constraints for non-gravitational wave observations, they consider a single bounded power law distribution with this particular normalization. That's all well and good. However, what we do in our work is that instead of considering just single bounded power law distributions just for positive and negative tilts of your power law, what I did with Dr. Reynabel Reyes is that, okay, let's consider both positive, negative, and gamma equals 0. That is, we're going to assume as well that, okay, what if we have a flat mass distribution? And in order to make things comparable, we have to calculate it as a double-bounded power law. So it's fairly similar to the single-bounded power law that was given before, same form, except the normalization differs significantly. And because of the difference in normalization, we also have to calculate the mass moments differently and much more specifically. Although generally they're just a function of Qmax, which is the maximum allowed mass ratio that we have for our distribution, as well as gamma, which is the tilt of our distribution. From here, we can also calculate a spread, and we just do this in order to make things comparable with the work done by Carr and collaborators. So given that we already have a mass distribution, we insert it here into the differential merger rate. And then from here, we can start calculating what our constraint will be. How will we constrain actually the quantities that we want? So the preliminary here is that, okay, at the mass distribution level, let's give us fixed grid of gamma from -10 to 10 arbitrarily, just to approximate, like, okay, so -10, +10 usually are actually overkill approximations for monochromatic distributions. And then as you decrease the tilt and you get it all the way to 0, it becomes flatter and flatter. And for systematic reasons, we should also check how our results change depending on if we change the width of our mass distribution as well, or Qmax. Then we are primarily calculating for the event rate of the mergers that we have. So NDET here is the event rate of mergers that we have for a particular detector, which is characterized by PDET. Delta R here, DR here, or rather RPBH, is the merger rate. So what we are just going to do is, okay, we're going to generate PDET for ET and LISA across the entire target mass and redshift range. And then in contrast to other studies which utilize IMR phenom D for their waveform templates, we're going to be utilizing IMR phenom XAS specifically in order to take advantage of the wide mass ratios in consideration. So the procedure is going to be as follows. We set the preliminaries, gamma, Qmax, and PDET for every single detector we're going to use, LISA and Einstein telescope. Then we evaluate NDET for all combinations of PBH and M sub C for both low redshift, so we're going to be integrating from 0 to 30, and for high redshift from 30 to, in our case, we set our ceiling to 300. And then finally, we take all of these NDET combinations and then just plot all NDET greater than 1. That is to say, if this combination of FPBH, M sub C, and all the other parameters generate a detection within 1 year, a simulated detection in 1 year, we count that as like the lower bound for the minimum testable abundance for that particular range of M sub C. And our results are as follows. So for low redshift, we see that, okay, in LISA's case, we have fairly robust constraints. We don't really have much movement. If gray here is the monochromatic constraints obtained by a previous study by De Luca, in comparison, they were using IMR phenom D. Our purple region here is what we got when we were using IMR phenom XAS. And overall, we really don't observe that much change in the behavior of the constraint. Okay, maybe at around gamma equals 0, there is a slight lowering of the constraint here, but otherwise, we really don't expect much of a change. Or we really don't see much of a change. In Einstein telescope, it's a bit peculiar because the IMR phenom, the monochromatic results extend the mass window all the way down to like 10 to the negative 4 solar masses. If you consider XAS, apparently the mass window actually shrinks. But overall, despite these differences, if we count only the changes in gamma, then there's not much change in the constraint behavior, at least for low redshift. Now, if we go to higher redshifts, it's sort of a similar story, except in the Einstein telescope case, we do see some fairly strange behavior as well, at least for once we approach gamma equals 1. Although, if you take into account the scales, it's just a widening of around 1 order of magnitude on both sides of the constraint window. So overall, I would say that at least our constraints are relatively robust, or the constraints are still relatively robust, even at higher redshifts. Since, especially if we look at it here, this is just another way of visualizing how the constraints change as we change gamma, or in this case, sigma, more or less the same thing. We see relatively zero movement for low redshifts, and then at higher redshifts, roughly the same thing, except, well, this fairly weird behavior at the Einstein telescope for positive values of gamma. Now, if we compare it to existing constraints, this is what it actually looks like. So here in gray, we have all the existing monochromatic constraints from HSC, Planck, mu distortion measurements, Lyman alpha, GW03 as well. And we see that there's relatively not much movement, even if we consider an extended mass distribution compared to monochromatic distributions. In fact, LISA, for the most part, LISA constraints are pretty much irrelevant given the current scenario. Now, we also look into its effects on the SGWB. And in the SGWB as well, we see some shift in the higher mass window, but otherwise, they're all fairly robust as well. In that you really can't make a distinguishing call whether or not the extended mass distributions changed much of the behavior of the constraints. Now, that's only when you account for extended mass distributions alone. You simply just change the phi. What if you change other parameters as well, given the assumption that you have a much larger pool of masses to choose from? So for that, we need to discuss, okay, what if your clustering behavior is modulated based off Q, or what we call the mass ratio? For that, we first need to discuss the premise of PBH clustering. So you have the definition of, so the probability of your PBHs to have neighbors is dependent on the nearest neighbor probability, which is given by equation 25, which is Poisson. More or less, this is just the definition of a Poisson distribution. So n is your average co-moving number of PBHs, and n of x is just the expected number of PBHs within that spherical volume. And then after that, you have the next to nearest neighbor probability, which is given by roughly the same thing if you assume a Poisson spatial distribution as well. Now, we define initial clustering for PBHs as the likelihood that those PBHs would form in some denser than average clusters at the scale of the next to nearest neighbor distance y. So you assume that you already have a binary that is separated by a distance x0. What you want now is to determine how close or how far the next to nearest neighbor of that binary is with this distance y. So the common model for modeling clustering, this is used as well in galactic surveys, is the Poisson model of clustering, which is given by equation number 27. Delta x here is your density contrast, at some point x, delta sub c is the critical density threshold, in this specific case for PBH formation. Now you can encode initial clustering then as an excess probability of formation. So this 1 plus C of R is an excess probability that you insert into your N of Y. That essentially tells you how much more or how much less are your PBHs relative to the population average. Now, to get an intuition of how we actually formulate the N of Y and insert it into the merger rate, because as you would see here earlier, there is an N bar of Y here that is related to the number of PBHs that are the neighbors of your binary. So to get an intuition of how we calculate for that, let's first start with equation 28, the previous one. And then we define Y as the characteristic co-moving separation between two PBHs with some total mass M total. Then we can define as well the average PBH number density given by small n, where the average distance is given by x av and is characterized by the average mass of the PBH mass distribution. And if we evaluate it simply by integrating and substituting the relevant quantities, we get this here, which is quite similar to how n bar y is formulated. So given that it's just more or less a simple substitution based off some certain assumptions about the co-moving separation of primordial black holes, then we can compute for n of y with a correlation function inserted into it. The correlation function that we use for this particular study that we did is the two-point correlator formulated by Auclair and Blachier, specifically for primordial black holes. This one is a fairly new correlator based off excursion set theory. And it has very nice properties in that, okay, instead of being agnostic to mass, you can actually define what the correlator is and define the masses for this particular correlator given by sigma 1 and sigma 2. Those define the masses of your primordial black holes. Lambda here defines the absorbing threshold for PBH formation. So it scales with delta C as well as sigma of R. And the sigma of R here is a variance scale between your primordial black holes that are a distance R from each other. And the others are just abbreviated terms for this expression over here. So now that we have a two-point correlator, we know how n of y is formulated. We can start building on what n of y should be functionally for our merger rate. We do that by defining the power spectrum of the PBH density perturbations. We define it here as a power law, specifically characterized by a cutoff scale k and a spectral tilt n sub p. This allows us to define the variance scale, sigma sub r, by equation 36. And here we just choose a window function that's top hat in k for simplicity. Now, our choice of n sub p is going to inevitably determine what is going to be our mass distribution. And we're going to utilize a result from De Luca, which relates the spectral tilt with the mass distribution. Specifically, the spectral tilt NP equals 0 is related to the mass distribution of gamma, characterized by gamma equals -1/2. So we extend that a bit and say that we have an ansatz that n sub p is related to gamma linearly and 1/2, at least for small values of n sub p. you cannot really generalize this to much larger values of gamma, not necessarily at least. So with that, we plug in everything together. And the second paper that I wrote applies the above model to constraints for merger-generated gravitational waves. So we have a local neighbor count now. We now call it N of Y and Q. And it's pretty much similar to N of Y that we have seen previously with the Poisson model, except now we have a factor of G here, which is determined by Q, delta sub C, and N sub P, and is given by equation 38. So one interesting property here to note is that apart from the parameters delta sub C and N sub P, G is fully determined, or rather its behavior is pretty much fully determined by the mass ratio Q. So in other words, depending on the mass ratio of the binaries that you will have differing clustering, you'll have differing clustering behaviors across your PBH populations. But of course, we first need to check how G of Q also responds to the different parameters that it has. So first we have G of Q as a function of delta sub C. And it turns out that it's fairly robust as well in delta sub C, except for fairly small values of delta, which is sort of expected because the smaller in values of delta that you go, the higher the probability is for PBH formation, which is going to also result in higher values of G. Otherwise, though, you have a fairly predictable power law slope across nearly all values of delta that we reasonably consider. And that power law slope is given by Q to the negative 6/5 based off numerical calculations. Now, it's also surprisingly fairly robust in N sub P as well. So regardless of spectral tilt of your primordial black hole density fluctuations, turns out that at least given our correlation model, G of Q is also not going to change in behavior at all, even if you change your power law tilt to be greater than or less than 0.01. Now, whether or not this correlates to changes in gamma, we cannot be too sure, which is why we stick, at least for the remainder of the talk, to values of gamma equals negative 1/2. Now, if we compare our model of N of Y with the Poisson models of N of Y for both the same power law distribution as well for monochromatic distributions, we see that more or less the most outstanding quality here is that your N of Y behavior changes depending on what the mass ratio is. So as mentioned, this is a Q-modulated clustering behavior. And in particular, if you have Q equals 1, your Q equals 1 binaries are actually much more densely clustered compared to even the usual Poisson binary, usually Poisson distributed binaries. Surprisingly enough, though, as you increase your Q, they become much less and less clustered, evidenced by lower values of N of Y. And because of this also leads to directly changes in how your PBHs are suppressed. Because the higher greater value of N, the lower value your S sub 1 is, and that leads to greater suppression. So in comparison to the monochromatic case, or in comparison to the usual Poisson case, your Q equals 1 is much more suppressed much sooner in FPBH compared to the usual Poisson case. In contrast, Q equals 32, Q equals 1000, much lower, much higher binary mass ratios would lead to much lower suppression factors, or rather much less suppression. And then here's the effect that it has on your constraint projections. So overall, it doesn't really change much for the higher mass binaries, but then as you get to the lower end of the distribution, you will see a slight
Hi,
opening.
5 minutes left.
Okay. You will see a slight opening of your mass window, which then suggests that your merger rate in this regime of masses is much higher compared to the standard that we observe for both monochromatic case and the usual extended mass distribution only case. This applies to both ET and LISA detections. We also observe the same as well for for higher redshifts. And surprisingly enough, as well for SGWB. Although for SGWB, the constraints merge quite quickly as you get to higher and higher masses. So to conclude, we basically have two major results here. First is that constraints are robust to changes in phi of m if you just take that into account, and if you only make changes to that part of the merger rate. Broad mass distribution modifications alone are insufficient to distinguish between your constraints. And then result number two is that if you combine those effects of EMDs with clustering, then it may lead to enhanced merge rate for lighter binaries. And that is if you have PBHs that exist and are clustered as per equation number 34, the model that we have considered, then the abundance threshold for subsolar